Now we come on to a lesson discussing a very important case, the database use case, which we noted that the first five use cases are classified with this, and many of the use cases use databases maybe less intensely. In general, that's one approach to search and query, although NoSQL is actually used for the largest search and query applications. And indices are a critical feature of this application because that allows databases to work fast. When we compare NoSQL with databases, some people like to call databases as having predetermined structure. That's true. You have to define the entity relationships, which is the meaning of the columns of the entries in the database. That's it's called schema on write because you determine that schema completely and rigorously ahead of time, and that allows highly optimized queries in the SQL language. Online transaction processing (OLTP), essential for the banking industry, is a good example where these traditional databases are good. When we're talking about these entity relationships, there's a little picture here showing a relation, which is a row of the table, and each member of the table has there are a set of attributes, which are the columns of the table, and each entry, each record has values for those attributes. The indices implies super good performance. Databases have long done incredibly high quality fault tolerance. People would not be happy if the computer crashed while their bank account was being processed, and that created incorrect accounts. Databases, traditional databases can scale, but they can't scale to the size that NoSQL can. These optimizations and fault tolerance algorithms do not have scalable parallelism. If we look at, say, bank accounts, I didn't actually find anywhere on the web telling me how big the data is. I sort of estimated maybe it could be up to a petabyte. That was if there were 10 to the fifth transactions, each of 100 bytes. That's over the time the data was stored, which will be many years. And then with 100 million people, you get a petabyte. You will see lots of discussions on in the internet and things about what's better, databases or these new cloud solutions typified by MapReduce, Hadoop, and NoSQL for storage. And it's not that databases are wrong or NoSQL is wrong. It's all a question of more optimization. Namely, there are problems that can make, which really require the rigorous fault tolerance of traditional databases, and problems like search that don't. If you have a crash in your search, you lose 0.01% of the data, you're probably not worried so much. So this is not a sort of very pejorative discussion when we compare these approaches. They really have very different optimizations. And so in some sense, everything can do everything. It's not surprising, but some of these approaches are better optimized than others for particular use cases. SQL itself, the language, is relatively controversial. Many people, actually including me, do not like writing SQL and find it less intuitive than other languages. And that is then has SQL replaced by what's sometimes in other applications called business logic, which is software that does the processing of the data and the searching through the data. If you go to the web, you'll see sometimes these comparisons between databases and NoSQL presented and MapReduce presented as a cost issue. Namely, if you have a terabyte per year, it might cost you $1,000 to $2,000. If you process it on a Hadoop cluster, that's $1,000 to $2,000 per year, but maybe up to at least an order of magnitude more than that for a commercial relational database. One reason for that is just the commercial software, like Oracle software, is very expensive. Another is the relational databases, because they don't have such an easy job optimizing the app, getting parallelism to get better performance. They tend to use more expensive servers than the commodity servers Hadoop uses. We'll see in the following slides the concept of ETL, extract, transform, load. That's how you stuff data into what's called a data warehouse, which is a collection of enterprises' data. And those ETL and data warehouses are an important part of the lingo of traditional relational databases. We'll also see on one of the slides an operational data stores, or ODS. Here's where we have this discussion of schema on write for relational databases and schema on read, meaning that Hadoop just reads unstructured data and creates structure on top of it. Sounds less efficient, and it is less efficient on some applications, but it scales very easily, and so the efficiency you lose from the predefined indices of relational database, you gain back from the ability to scale to large number of nodes on commodity clusters, which are very cheap. So in the case of Hadoop, you tend to process the data in its native form, do all transformations after you read it in, and that's why you don't have this pre-processing step of ETL for Hadoop. And they like to summarize it this, that relational databases are good for known unknowns, repeating an analysis, and Hadoop is good for unstructured search, exploratory research, where you're looking for unknown unknowns, exploration. Here's a example of a workflow. The business intelligence is your final answer. What you want from your analysis is the result of the X Informatics application, and that is shown here with data coming in from the bottom. It's an ODS. Then we have the ETL step, which is just time consuming because it's again not as it's not scale as well as Hadoop. And then it either goes to OLTP or to the data warehouse. The OLTP databases adds its data to that from other data stores, and then you get the data warehouse where you do the transformation, which may not be so efficient, and you do the query. So that's traditional architecture. Even more simply, it's shown here. ETL from diverse data sets, put it into the warehouse, and then you do analytics on the warehouse, getting business intelligence. You also do transformations to get data products. This shows a Cloudera solution along the same lines. We have the ODS at the bottom here, OLTP, online transaction processing here again, the ETL taking that data, feeding it into the Cloudera engine. Cloudera is a company that effectively packages Hadoop for particular applications, and can access the data warehouse, but also go directly from the data through the new SQL storage to very efficient data analytics. If you go to the big companies like IBM and Oracle, they were always almost by definition offer everything. So if you look at their platform, it has Hadoop, it has data warehouse, it has streaming, it has all sorts of optimization, it has visualization and things like that. And it's not, in this world we live in, simplicity is sometimes good, and these do everything applications, which is sort of what the bigger companies probably must have to offer so they can actually help anybody. They may or may not be as attractive for a given small company trying to solve a very particular problem. Might be better to hire a bright young student, bring up a dupe, and then chug away. Here's the same picture from Oracle, because Oracle, IBM has DB2 as its database. Oracle has the Oracle database, which obviously both of those are leading products in the field. And again, Oracle says it does big data and transaction data and metadata and unstructured data. And that's the middle of this circle here. And then around that, you have things like security, life cycle, etc. And this is the enterprise architecture framework, which is again doing everything for everybody in a possibly, at least not easy to understand fashion for any one case.